Let's imagine we have some general three-dimensional shape of something, and we've got a coordinate system, and we want to define the center of mass of our abstract object, whatever it is, some general shape. And we're going to use whatever our arbitrary coordinate system is. Well, what we're going to do is we're going to take the object and break it down into little tiny pieces. So break it down into very small pieces, each piece with a little mass. We'll call it delta m sub I. And then determine what's the coordinate, what's the position of that little delta m sub I. So we'll have a position vector from our coordinate system to our little tiny mass, and that will be the position vector r sub I. And then we'll just treat it like a collection of point masses. So we'll take the total mass. Well, what's the total mass? The total mass will be the sum of all of these little tiny masses, delta mi. And then the total mass times the position of the center of mass will be the sum of all of the individual positions of the tiny masses, r sub I, delta mi. Now that would work to some extent. The larger we choose our delta m, the less precise this result will be. But the smaller we choose our delta m, the more precise this will be. Well, how are we going to make this exact? Well, what do you think? We've done this a number of times. What do you think? We're going to make these little delta m sub i's infinitesimally small. And what happens when this gets infinitesimally small and we have to add up over an infinite number of infinitesimal things? What happens to the summation? What happens to the sum? It becomes an integral. So what happens then is this will become the integral of r dm. And what do we integrate over? Well, this is a little tricky. This is not just like integrating under a single curve and finding the area. This is a little bit more complicated. This is a three-dimensional integral, and we need to integrate to add up all of the little delta m's, all of the little dm's over the entire volume. So this is going to be a volume integral. So before, when we were looking at work and we had a path that we were integrating over, and that was a path integral or a line integral, this is going to be a volume integral. We need to integrate over an entire three-dimensional volume in general. We could have a flat surface, which would be a two-dimensional volume integral. Sorry, that doesn't make sense. A two-dimensional surface integral if it was something like a very thin mass, like a sheet or something of mass, or if it was a line of mass, like a wire or something like that, we could have a one-dimensional mass integral. But in general, it's going to be a three-dimensional volume integral, integrating over the entire mass, and for every little mass element, we multiply it by it. Whoops, sorry, lost something here. The position vector, multiplying by the position vector measured from our coordinate system. We integrate that, and that will give us the total mass, which is, and then what would the total mass be? This would become the integral of all of the little individual masses, the total mass, times the position of the center of mass. Okay, very, very good. Let's take a look at an example of this. Why is this so important? Why do we even make this definition? What use is it? Well, let's take a look at an example. Let's imagine that we've got either a collection of point masses or some extended object. The point masses each have a mass m sub I. The extended object we break down into little infinitesimal tiny masses d sub m. Let's figure out what is the gravitational potential energy of each of these systems. Let's imagine that we've got some low zero height position. So this is where y equals 0, y equals 0. This will be where our potential energy is 0, where the height is 0. What's the potential energy of this system? Well, it'll be the sum of the potential energies of each point. So the total will be the sum of the potential energy of each particle, which will be, well, what's the potential energy of a single point mass? It's mg times the height, mgh, or in this case, we'll say mgy sub I. mgy sub I. Well, what about this case? Well, in this case, again, we'll measure it from here. The total potential will be the integral of the infinitesimal potentials, which will be the integral of each little mass, dm, g times the height of that. In other words, the integral of gy dm. Okay, great. Well, let's look over here. I forgot to sum, so we need to sum this then. Oops, sum. There we go. If, and we'll assume that this system is m sub I, we'll assume that this system is in a uniform gravitational field. In other words, g is constant for all the particles. If it's not, if g actually varies, it's a little more complicated. G is actually part of the, this would be g sub I. But we'll assume that g is constant for the same value, constant for all of the little masses. So we can pull that out, and what do we get? This is equal to the integral of g, equal to g times the sum of mi sub I. But what's that? That is exactly the right-hand side of what we determined to be the total mass times the center of mass position for the y-coordinate. So this is g times the total mass times the position of the y center of mass. In other words, we could write this as mg y center of mass. And then what do we get on this side? Well, again, assuming g is constant, pull the g out. This is g times the integral of y dm. But what's that? That is exactly the y component of the center of mass for a continuous system. So this is g times the total mass times y cm, or mg y cm. Sorry, I don't know if you can hear the voices outside. I think a class let out. There's some people outside in the hallway. So let's look at this. What do these mean actually physically? What do these tell us? Well, this is basically telling us that the energy of the system we can think of as basically existing with the whole mass at the position of the center of mass, the total mass at the location of the center of mass. If we had a single point mass with a mass equal to the total mass of the system at the position of the center of mass, what would its gravitational potential energy be? Total m times g times the height of the center of mass. It's exactly the same as the extended system. So the potential energy of the extended system is exactly the same as if we had a single point mass located at the center of mass with a mass that's the sum, the total mass of the whole system. Likewise, that's exactly what this is telling us. The total mass times g times the height of the center of mass. Well, this is something that happens over and over again, that when we are looking at a system, we can very, very often treat it as a point mass located at the center of mass of the system. Now, that's not taking into account relative motion or something like that of the point masses around the center of mass, but it is taking into account at least part of what's going on. And in terms of the potential energy, it is giving us exactly that result. All right, very, very good. Let's take a look at a simple example of what this does for us. Let's imagine that we've got a small mass, so a point mass in this case, and I have it suspended on a string here. If I were to release it, what's it going to do? Well, it tries to return to its equilibrium position. Remember, there's a restoring force that is trying to get it back to where? Its lowest position. Remember when we were looking at potentials and we had, say, a bowl-shaped potential? Where does the object try to go? It tries to go back to its equilibrium position where the net force acting on it from the external forces are zero. So here, it tries to return to equilibrium at the bottom, at the lowest point. Well, what if we hold some object? What if we have some object like this and we suspend it? So I'm going to put a little pin through it here. What does it do? If I hold it like this and I release it, I hold this point here but allow the object to rotate, what's it do? Well, it rotates until the center of mass is directly below the point of support. In other words, the center of mass is at the lowest point. Well, what if I hold it at a different point? What if I put it over here? Say I suspend it here. Well, then what's going to happen? Let's make this nice and easy to rotate. Okay, I put it over here, what's it do? Well, again, it moves until coming to rest so that the center of mass is directly below the point of support. What if do it on the other side? What happens then? We see that again, it moves until the center of mass is directly below the point of support. So we have a very similar relationship to what the system does when we have an extended system with a center of mass compared to a simple system, a point mass, in terms of the motion in an external field, always trying to return to the point of lowest potential energy. And in terms of the system, that means the center of mass coming to the lowest point. Okay, very, very good. One more point I'd like to go over in terms of this definition, how we might use this when we apply it to some extended system. Let's take a look at that. Let's imagine that we have some extended system, and I've drawn in 5 masses here. Mass 1, 2, 3, 4, and 5. But you could do this with as many as you want. You'll see how this extends very easily. The total mass, the sum of all the masses, times the position of the center of mass of the system is then m1r1 plus m2r2 plus m3r3 plus m4r5, 4 plus m5r5. But let's just look at these in terms of parts of them. What is m1r1 times m2r2 if we just wanted to look at those two? Well, that is the total mass of just m1 and m2. I'll just call that m12 times the center of mass, rcm, of just m1 and m2. So this is the way we would define the total mass times the center of mass if we only had 2 objects, just mass 1 and mass 2. Well, what about this? Well, that would be the center of mass that we would have defined if we only had m3, m4, and m5. So this we might think of as m123 times our center of mass 3, 4, 5. 3, 4, 5. 3, 4, 5. 3, 4, 5. And we are adding them together. Well, that's a very interesting result, and you can see how you might extend this so that if we have, say, 2 parts of our system, this part and this part, the total mass times the center of mass of the whole system is the mass of one part times its center of mass plus the mass of the second part times its center of mass. So basically, if you have different parts with different centers of mass, you can find the center of mass of the entire system just by taking each individual part, take its mass times its position of the center of mass, its mass, its position of the center of mass, add those together, and that's going to give you the total mass times the position of the center of mass of the entire system. Well, that's a very, very nice result, which allows us to basically think of even if we have something that is not exactly a point mass, maybe we have some somewhat extended object, but not a huge object, we can think of it as a point mass and just imagine what's the center of this object and put it into our equation to determine the center of mass of a more extended system. That's very, very useful. Okay, excellent. What if our objects are not stationary? What if they're moving? What if M1 is moving over this way and M2 is going that way and M3 is going that way? What if they actually have some velocities? What is that going to do to the center of mass, and how can we incorporate velocities into this discussion? Let's take a look.